introduce Professor Vincent Wong and chair this session. Thank you very much.
Thank you very much for kind introduction. Am I audible? Am I audible to you?
Yes, sir. Very loud and
Thank you
clear.
very much. I welcome all of you to STI 2020, the second in the session, a conference on sustainable technologies for industries. We are very fortunate to have many distinguished speakers in this conference. So today in this session, in the second keynote space, we have Professor Vincent Wong, and he's from British Columbia. He received his BSc with distinction from the University of Manitoba in 1994. MSc degree, usually in Canada, they do not call it engineering degree, applied science degree from the University of Waterloo in 1996, and PhD from the University of British Columbia in 2000, all in electrical engineering. He has a very distinguished career. Dr. Wong is an executive editor, editorial committee member of the IEEE Transactions on Wireless Communications, an area editor of the IEEE Transactions on Communications, and IEEE Open Journal of the Communications Society, and an associate editor of IEEE Transactions on Mobile Computing. He has served as a great editor of the IEEE Journal on Selected Areas in Communications and IEEE Wireless Communications, and was on the editorial boards of the IEEE Transactions on Vehicular Technology and Journal of Communications and Networks. He is an IEEE Communication Society Distinguished Lecturer 2019-2020. He is the chair of the IEEE Vancouver Joint Communications Chapter and has served as the chair of the IEEE Communications Society Emerging Technology Subcommittee on Smart Grid Computing. He is a fellow of IEEE. He has about 15,000 citations as of 6:53 a.m. Bangladesh Standard Time, 18 December 2020. I am sure it might have crossed 15,000 as well. He has already given 14 PhDs and at least 24 dinner party pictures. So those who are thinking of doing PhD, he is the right supervisor. He will be giving a lot of dinner party. I have said he has enormous number of publications. If I look at the rate he has been producing, it is really enormous. In 2021, he has already one paper. In 2020, he had 17 papers to his credit. In 2019, it was 12 papers. In 2018, 16 papers. In 2017, 15 papers. In 2016, 11 papers. So low, many publications. So I take this opportunity of inviting Professor Vincent Chang to enlighten us, to enlighten the community with his keynote speech.
Thank you very much.
Professor Vincent Chang.
Thank you very much for the kind introduction. Before I begin, I want to ask one question. Is for my talk, is it 35 minutes or 40 minutes before the question?
So it is total 45 minutes. So
Okay.
you can keep some 5 minutes for
Sure.
queries, questions, okay?
Okay.
Thank you very much.
Okay. So can you see my screen?
Yes.
Good. Okay, perfect.
You can see it very well, yeah.
So again, thank you very much for the kind introduction. It is unfortunate that due to COVID-19, I cannot come in person to Bangladesh to give a talk. Bangladesh is one of the countries that I really want to visit in near future. And I have worked with some wonderful graduate students from Bangladesh as well. And any of you who are interested to pursue a PhD degree in Canada, in western part of Canada, you're very encouraged and welcome to apply to our department as well. So the title for the presentation today is related to uplink access for wireless communication systems. I understand that this conference is in the area of sustainable technologies. And the first keynote speaker, Professor Claudio Canizares, already gave an excellent talk about some of the background related to microgrid from the power system or smart grid perspective. And what I'm going today is to give you some of the insights or the way I look at how we can support sustainability in the area of communications and networking. So the work that I'm going to present today is a joint work with my PhD student, Rui Kwang, and also my collaborator, Robert Schobert. So the first slide showing here is related to some of the techniques related to not the 5th generation, but the future generation 6G wireless systems. In the right-hand side of the figure, you see that there are lists of applications or use cases. Apart from the traditional smartphones applications, in the 5G and also in the 6G systems, there will be new applications related to autonomous driving, drones, UAVs, various types of extended augmented reality applications, smart city. People also talk about smart mega city as well. Many of them, they have different quality of service requirements. Some of them require a high data rate, while some of them, they require a low latency and a very high reliability as well. For the figure on the left-hand side, it shows some of the technologies related to the 5G and also the 6G systems. Some technologies, such as massive multiple input, multiple output, massive MIMO systems, they are important in 5G and also will be important for 6G as well, especially when we move into millimeter wave as well as terahertz communications. Apart from that, there will be new technologies such as the use of intelligent reflection surfaces, IRS, which can further enhance the spectral efficiency in a network. We have various types of devices. Some of them are controlled by human beings. Some of them, they are autonomous. Many of them, they need to send data to the base station. In the network side, in a base station, it will not just, a base station will not just be an element to send data. At the same time, the base station may also perform sensing and also perform computation as well. So the base station will have the joint sensing, communication, and also computation capability. In a core network, which is the cloud in the middle of this figure here, nowadays in many networks, service providers have already started to deploy the use of software-defined networking, SDN, and network function virtualization as well. People envision that in future networks, machine learning or artificial intelligence, AI, will also be an important technology in the future networks. So you notice that in this figure, I used the acronym AI multiple times in the core network and also in the access network. And in this presentation, what I plan to do is to introduce one technique related to deep learning, which a lot of researchers, including me, believe that it will be an important tool for the design and analysis of different types of algorithms in wireless networks. So let me make sure that I can go to the next slide. Okay. In the area of machine learning, basically, it can be divided into 3 types: supervised learning, unsupervised learning, and reinforcement learning. For supervised learning, what we need in the beginning is a data set which we are given the input. We already know what is the corresponding output, or what people call the label examples. So later on, once you have already trained the neural network, when you have an unknown input, then the neural network will be able to decide what is the corresponding output. For the second type of machine learning is unsupervised learning. In this case, we do not have labeled data, but instead we are given a data set, and based on the data set, the neural network will be able to determine the corresponding hidden feature related to the data set as well. So typically, those features are actually very important for classification and also for different types of clustering. In this presentation, my focus is actually related to the third type, which is reinforcement learning. Reinforcement learning, in a nutshell, is a technique that is used to solve sequential decision problem. When you see the word sequential here, it means that in each time slot or in each decision epoch, we need to actually make a decision. And what the agent needs to do is it wants to choose the action or make a decision in an intelligent manner so that in the longer term, it can achieve its objective. And typically, in reinforcement learning paradigm, that corresponds to maximize the accumulated reward. In the past 5 to 6 years, there are a lot of advances in deep learning and also in reinforcement learning. In deep neural networks, there are different types of network modules, such as long short-term memory that can efficiently handle different types of temporal correlations. There are other types of modules, including pointer network, which can solve combinatorial problem or types of problems which are actually NP hard, and pointer network is actually a good tool in terms of having a lower computational complexity than some of the techniques that require to solve the problem and obtain a global optimal solution. For deep reinforcement learning, it is essentially a combination of deep learning and traditional deep reinforcement learning. Different companies, especially Google DeepMind, over the past few years, have developed different types of deep reinforcement learning algorithms. And if you follow the news, you will notice that many of those frameworks have already defeated some of the professional chess masters. Also, in different types of online games competitions, also became the champion as well. Deep reinforcement learning has also been applied to study different types of problems in wireless communications and networking. So before I describe deep reinforcement learning, I will first give a very high-level overview about what exactly is reinforcement learning. Reinforcement learning is a framework to solve sequential decision problem. So the way it works is that in each time slot, there's an agent, which is a decision maker. What the agent needs to do is first obtain some observation related to the environment. So it will obtain the observation, which we give a name called a state, which is the state information. Based on the current state information, the agent will choose an action. And the action in this case will actually has two effects. The agent, based on the current state and the action chosen, will receive a reward signal coming from the environment. At the same time, the next state also depends on the current state and also the action chosen by the agent as well. So in the next time slot, the agent moves to a different state and the agent repeats this process. Once it is in a different state, it needs to choose another action and receive another reward, move on to the next state, so on and so forth. If we consider the decision problem, which has finite time horizon, in this case, the agent would like to maximize the cumulative reward. On the other hand, if the time horizon is infinite, what the agent will do is it will try to maximize the discounted reward by introducing a discount factor for each reward that it receives in future. Deep reinforcement learning has been applied successfully for different types of problems. But one of the drawbacks in deep reinforcement learning is that it suffers a term which is called curse of dimensionality. What it means is that if the state space is too large or if the action space is too large, then it will take a long time for the algorithm to converge. And a few years ago, researchers or colleagues in the machine learning community noticed that it can combine deep learning or some of the techniques in deep learning with reinforcement learning. And we have coined the term deep reinforcement learning here. The advantage of using deep reinforcement learning is that this time, if you refer to this figure here, we have a set of DNA modules. The main function of the deep neural networks DNA modules are to let us approximate the corresponding state value function. So we emphasize the term approximate here. If we actually design the DNA modules good enough, then the approximation will actually be very close to the actual optimal solution by compared to the small scale problem. And based on that, deep reinforcement learning, that is reinforcement learning combined with DNN, it can handle different types of problems which have a large state space or problems which have a large action space. And that's why deep reinforcement learning, there are many applications in this area, not just in robotics or in signal processing, but at the same time, there are now different applications in wireless communications and networking as well. In a nutshell, for deep reinforcement learning, it is a useful technique to be applied in wireless communication systems. And the reason is as follows. For the past 20 years, many of us, when we work on wireless communications and networking, we design an algorithm or we formulate an algorithm by formulating as an optimization problem. Even though by formulating the problem as an optimization problem, we can obtain a global optimal solution in some cases. But the potential drawback is that the parameters that were used in the optimization problem many times also require an estimation. And when we talk about estimation here, there's always an error. So in practical systems, even though we may be able to formulate the problem as an optimization problem, but the solution may not be really the global optimal. And at the same time, some of the system parameters also change over time as well. And some parameters, such as the mobility pattern of the users, may actually be difficult to estimate in practice. So deep reinforcement learning can actually handle those situations. And apart from that, compared to supervised learning, another advantage of using deep reinforcement learning is that we do not require a data set a priori for us to actually execute or invoke the algorithm. But instead, for deep reinforcement learning, what we need is corresponds to the transition history of the system, or in the deep reinforcement learning term, that is called the replay memory. So what I'm going to do now is I will spend another 10 to 15 minutes to actually give you an example of how we can apply deep reinforcement learning to solve a problem in the area of uplink access in IoT systems. But before that, I'll just give you some motivation about this piece of work. As we mentioned earlier, in the future 5G or 6G systems, there will be different types of sensors. The sensors may include smart meters. At the same time, it may include some of the devices at home. It may also involve some of the sensors, such as surveillance camera, that may need to send data at a relatively high data rate to the base station. If you look further, UAVs or drones, you can also treat that as sensors as well. If they are autonomous, they also need to send images or videos to the base station periodically. Many companies have now developed products related to IoT. Some of those products may be related to smart home. Some of them may be related to smart city, intelligent transportation systems as well, and also intelligent or smart agricultural area by deploying sensors into a farm as well. The key message here is that there will be different types of sensors, and different sensors may have different capabilities and also different requirements. Some of them, many of them will say we'll only send packets which have a small data payload, and the traffic may not always be periodic. Some of them may be bursty as well, and different types of sensors may have different requirements. So what we want to study is that how we can actually design a technique which can efficiently support the uplink access for large types of different types of sensors. In the third generation partnership project, 3GPP standard, which is a standardization body to standardize wireless cellular networks, including the long-term evolution LTE system. In the past, they have standardized a technique which is called a ground-based uplink access. And that is mainly used for human-type communication devices, such as our smartphone that we use typically. In this particular technique, which is the ground-based uplink access, the main idea is that before the device sends data packet, it needs to have multiple signaling control message exchange between the device and the base station before you can actually send the data packet. This technique is perfectly fine if we focus on smartphones or any different types of human-type communication devices. But then if we are going to use that to support IoT devices, which may only need to send a few small packets, then the overhead may be large. And for some of those devices which have a stringent delay requirement, the access delay may actually be long as well. And that's why in the 3GPP standard, recently, to use ground-free auto access to perform data packet transmission, it needs to select a pilot sequence for channel estimation as well at the base station. If multiple devices select the same pilot sequence at the same time, then there will be the signals will interfere, and there will be what we call packet collision, and there will be decoding failure at the base station. So in this case, it is important that we need to come up with a technique that can allow distributed pilot sequence selection for different devices. Apart from that, because different IoT devices have different quality of service requirement, including throughput as an example. So we want to make sure that given the limited radio resources, we want to support a large number of devices within a given area. There are many, there are different types of techniques that have been studied in the research literature. I only list 3 of them here, but many of them, they require the base station to actually do some coordination to resolve packet collision. Those are actually good techniques, but at the same time, because it requires the base station to involve the packet collision, the overhead can still be high and the delay can still be long as well. So in this piece of work, what we want to try to study is that we want to figure it out whether or not we can design a distributed pilot sequence selection algorithm so that we can have a high throughput and different IoT devices can provide their own, support their own quality of service guarantee. And what I'm going to do now is to actually provide you first the centralized problem formulation, and then show you the corresponding formulation by using deep reinforcement learning. So the system model is actually as follows. So I will just briefly go over that, but I think as for the presentation, the main idea is to for you to actually get a flavor of the work. If you cannot follow the notations, that's perfectly fine. But I think the main idea is actually important. We consider that this is a time-slotted system. There are n users in the system, and we consider one base station for now. There are k pilot sequences in total, and we assume, of course, the number of users is actually much larger than the number of pilot sequences here. Each user, whenever it has a data packet to send, it will select one pilot sequence among within this set here. So if user n or device n chooses the k pilot sequence, then this binary variable here will be equal to 1. Otherwise, it will be equal to 0. And we have this particular constraint here, saying that for each IoT device n, because it can only choose either one of the k pilot sequences, or it can choose not to transmit in this particular time slot. So in this case, this summation here is always less than or equal to 1 in this context. And we also considered the fact that if we just focus on the last inequality here, on the left-hand side, we have the average throughput of the device. And on the right-hand side, we have the corresponding average throughput requirement. Remember that different IoT devices may have different capabilities. There may be one IoT device which is a smart meter. We may have another IoT device which may be a surveillance camera, which have different throughput requirement. And these devices are all under the coverage of the same base station. So we want to make sure that different devices, we can support the corresponding throughput requirement. So if we want to formulate the problem in a centralized manner, we can formulate the problem such as this one. We may want to maximize the aggregate throughput, which is the time average throughput among all the devices, subject to the constraint that for each user or for each device in a particular time slot, it will only choose one of the K pilot sequences or choose not to transmit. At the same time, for each IoT device, we need to set aside the long-term throughput requirement as well. So notice that this is a very nice stochastic network optimization problem. The expectation here with respect to the arrival of the data packets in this case. And this is a combinatorial optimization problem because the random variables here, G and K, they are binary. And there are techniques which will allow us to obtain a global optimal solution. For example, by using stochastic network optimization, or by using Lyapunov optimization, by introducing virtual queues. But in our work, what we want to do is we want to not come up with a centralized technique, but we want to come up with a distributed technique. So what I'm going to do to show you in the next few slides are how we can look at this problem, the same problem, by using deep reinforcement learning. And later on, when I show you the results, I will compare the scheme based on deep reinforcement learning with the centralized approach by solving this particular problem here. So now we move on to look at the same problem, but by looking at this problem as a deep reinforcement learning problem. This time, we need to introduce some of the state information. So first of all, we have this information here, which is related to the outcome in the previous time slot. So this variable n sub k, it has one of the three values. It is equal to 1 if it is in the previous time slot, the k pilot sequence is only used by one particular device or by using one user. It is equal to -1 if in the previous time slot, multiple devices use the same pilot sequence. So in this case, the second one implies collision. The first case corresponds to successful packet transmission. And the third case is that in the previous time slot, no devices use the K pilot sequence for transmission. Since we are considering uplink access, so the base station has the complete information. So the base station can obtain all this information related to the K pilot sequence, and it will send this information by broadcast to all the devices at the beginning of each time slot. And for each device, so notice that in my presentation, when I talk about user here, user also corresponds to an IoT device. So the IoT device maintains a state vector, and this is the local state vector. This vector has k+1 elements. The first k elements correspond to the decoding state in the previous time slot, and the last element, which is shown in yellow color here, is the average throughput of device n up to time slot t. And finally, the base station maintains the global state information. And the global state information includes the decoding states of all the in the previous time slot, as well as the average throughput of all the devices under the coverage of this base station as well. So in this slide, the terms that I introduced are the local state of each user and the global state maintained by the base station. Since this is a decision-making problem, it's a distributed approach. For each device in each time slot, the device has to choose an action. The action corresponds to either the device will choose one of the K pilot sequences for select one of the K pilot sequence, or the device will choose not to transmit in this particular time slot. And I use the vector A here to denote the joint action vector of all the users in this case here. And in our framework, we need to introduce a reward signal. And all the devices or all the users receive the same reward. And the reward signal here is a summation related to the successful transmission of each user. We have the out of n hat, it is equal to 1 if the packet by user n has been successfully received by the base station. It is equal to -1 if device n encounter packet collision. If device n did not transmit in this time slot, it is equal to 0. So the first term is related to whether or not in the current time slot, based on the action chosen, whether or not different users, whether their packet transmission is successful or not successful. The second term, which is shown in this shaded color here, corresponds to whether or not in the current time slot, the average throughput requirement is satisfied or not. If the average throughput requirement is satisfied for user n, then this term will be equal to 0. If the throughput requirement is not satisfied, then there will be a penalty. And the penalty is actually proportional to the difference between the current average throughput and the average throughput requirement in this case here. So if I want to formulate the problem as a decision-making problem or as a reinforcement learning problem in particular, the typical way or one way to look at that, if you look at that from a single agent deep reinforcement learning problem, it will be the figure like this here. Each device at the current state and also given the current action chosen, we need to determine a function which is called a Q values, or in other books they call it state action value, Q value. And once the Q value has been determined, then given the current state, the device will be able to choose an action which maximizes this particular Q function here. But then if the state space is small, if the action space is small, there's no problem to actually solve or actually learn what is the corresponding Q value function. But then if the state space is too large or the action space is too large, then it is difficult. And that's why people come up with deep reinforcement learning technique. And one of the architectures is as follows. This time, the input corresponds to the transition history of the Markov decision process. That is, in the previous time slots, what are the states, the actions chosen, and the reward signal as well. And we'll use this historical information or this transition history as the input to the deep neural network modules. And the output of the deep DNA modules corresponds to the approximation of the Q values here. And based on that, the device will again be able to determine what should be the action that I choose based on the corresponding current information, current state information. And before I move on, I will also emphasize that there are two types of deep reinforcement learning problem. One is called a single agent, and the other one is called a multi-agent. And I guess the idea is actually simple to understand. Single agent corresponds to the fact that there's only one device or one decision maker that needs to interact with the environment. On the other hand, when we talk about multi-agent case, we have multiple devices that need to maybe coordinate related to the action, and it is interacting with the environment. In our case for uplink access, we formulate the problem as a multi-agent deep reinforcement learning problem, simply because we have multiple devices and they want to really coordinate the uplink access so that at the end, everybody can transmit, and at the same time, they can all satisfy the corresponding throughput requirement. In multi-agent deep reinforcement learning problem, it is still a very active research area, even in machine learning. And there are many issues that you need to deal with. One of them is related to what people call non-stationarity. And non-stationarity here implies the fact that if I'm an agent, during the training phase, that is the phase that I have not obtained the policy, I need to learn what is the corresponding policy or what kind of actions I should choose. Since we are actually working in an environment that there are other devices or other agents, different agents will also try to learn what should be the policies. So in this case, for non-stationarity here, it means that if different agents keep on changing their policy, then there's always a chance or a case that the algorithm may not converge. So in this case, there will be an endless cycle of actually changing the policies. And so we need techniques to actually handle the non-stationarity. And one way to handle non-stationarity is that you actually try to obtain the global Q value, which is the one showing here. And the global Q value is a function which depends on the global state information and also the joint action of all the devices. But then if you use the global Q value, the drawback is that it will lead to a centralized approach. But in our case, we want to have a distributed solution. On the other hand, if we consider the local Q value, the local Q value here, it is a function which depends on the local state information of each device and also the local action by the device as well. The advantage of using the local Q value is that it can lead to a distributed decentralized policy. But the drawback, as we mentioned here, it may lead to a non-stationarity issue. So what we want is the fact that we want to come up with a distributed scheme that can handle non-stationarity. And the main idea is that we can actually do that. And what we need to do is we want to have the training part to be done by the base station. So we have the centralized training by the base station. And each IoT device will actually obtain the corresponding parameters, learnable parameters, and then just execute the corresponding local distributed DQL algorithm. And given the remaining time, I will just highlight some of the important elements in different modules. One of the important thing is how we can relate the global Q value with the local Q value. That is, the global Q value depends on the global state and the global action, while the local Q value depends on the local state and also the local information as well. And what we want to achieve is that for an action chosen by a particular user, if this action leads to a large global Q value, this particular action should also lead to a large local Q value as well. So initially, what it means is that it is monotonic. So what we want is an equation, something like this. We want to have a monotonic equation that is in this particular form here. On the left-hand side, we have the global Q value, which depends on the global state and the joint action. On the right-hand side, we want to come up with or determine a function f, which is monotonic. And that only depends on the local Q functions here. And this particular monotonic function should satisfy the condition that when we take the partial derivative of this function f with respect to the local Q value, this is always positive. And this is what people call in machine learning, they call value decomposition or factorization of the global Q value. And we actually use this technique in our work for uplink access. So once we have this part, we can actually approximate this particular monotonic function f here by using this particular function, by using a technique called multilayer perceptron, MLP, which is a module in deep learning. And based on that, what we need to do is we need to determine a set of weights and also a set of biases. And this function, lowercase h here, is simply a sigmoidal function in this particular function. So now, to give a high-level description about the proposed module, this is actually what is being executed at the base station. The base station here will maintain in the left-hand side the global state information. Based on that, it will determine the corresponding weights and the biases by using the fully connected layer and to determine the weights and biases. Apart from that, the base station will also maintain the deep recurrent Q network for each IoT device. So if we have n devices, in this case, there will be n local Q modules here. And the local Q values will serve as the input to the multi-layer perceptron. And the output of the LMP network, in this case, corresponds to the global Q value. And what I'm going to do in the next two slides is just to give you a high-level overview about what is in each deep recurrent Q network DQL module. So these modules are actually maintained at the base station, and each IoT device also has one as well. The deep recurrent Q network has input layer, LSTM layer, and also the output layer as well. The input layer corresponds to the local state information, followed by multiple LSTM layers in order to learn the corresponding temporal correlation. That is what happened in the previous time slots related to the state and also the action, followed by the corresponding output layer. And the output layer here has two fully connected layers, and in the middle we have one rectified linear unit. And this is also another universal approximator for us to approximate the corresponding local Q value in this case. And given the remaining 4 minutes I have, I will just show you some of the results. And I will show you, as I mentioned earlier, we first formulate the problem by using stochastic network optimization, which is a centralized approach, but that is an optimal scheme. So we're going to use that to compare our decentralized scheme. And we also compared our proposed scheme with 3 other heuristics as well. Those are the references showing here, based on dynamic access class barring, acknowledgement-based scheme, and also the random selection scheme. So in this figure, the x-axis corresponds to the time slot, the y-axis corresponds to the average aggregate throughput. The first line, which is in red color at the very top, that corresponds to the optimal scheme. The optimal scheme is the one by solving a centralized stochastic network optimization problem here. Our proposed scheme is the one which is shown in blue color. As you can see, our scheme is a decentralized algorithm by using deep reinforcement learning. It has good performance compared to the global optimal solution. And some of you may ask, there's a 15% gap, and why there's a gap instead of having a 99% performance. The main reason is that because we are using a deep reinforcement learning network to actually approximate the corresponding state value function or the Q value function. So in this technique, even though this is a decentralized algorithm, because we need to use approximation to actually handle the case that we want to have a decentralized algorithm. And at the same time, we also use MLP network to actually approximate the monotonic function f as well. So that's why those approximation will lead to this particular gap here. But at the same time, results here show that our results have a better performance compared to 3 other heuristics. Apart from that, I will also show you the results that we mentioned earlier. Different devices may have different throughput requirement. So in this result, it shows that I divide the number of devices into 3 groups, and then I simply set a throughput requirement for each group. And the results in this figure shows that at the end, different users in different groups, they can always set aside the corresponding throughput requirement. So for the last 2 minutes, I will just show you 2 pieces of work quickly. And the main idea is to show that deep reinforcement learning can be applied not just in uplink access, but also in other problems as well. So this problem is related to data offloading in mobile edge computing system. When there's a new task arrive, the device, which can be a smartphone, it can be a tablet or any device, decides whether it wants to handle the task by actually using its local CPU or offload the task to the corresponding mobile edge computing node or fork node. And we can actually formulate the problem by using single agent deep reinforcement learning, where the state information of the device corresponds to the task, the size of the task, some of the queue information in different fork nodes. And we can actually use that, come up with the corresponding single agent deep reinforcement learning problem to actually solve the problem and obtain a good solution. And the details can actually be found in an accepted paper in IEEE Transactions on Mobile Computing. And in the very last slide, I will just show you that in the first keynote speaker by Professor Claudio Canizares, he has already shown you many interesting works about microgrid. And this one, I will also show you that in my group, I also have students work in the area of smart grid or energy system. And I collaborate with Professor Christine Chen, who is a domain expert in power system. So in this piece of work, what we did is how we can actually use deep reinforcement learning problem to study demand response in power system. the main challenge here is the fact that this time we also need to handle the case that there are constraints in the distribution networks. We formulated the problem by using single agent deep reinforcement learning combined with an active critic technique and also obtain a good performance. Compared with the case that we do not perform scheduling, and results show that the proposed scheme can also have a fast convergence and also have a lower cost as well. And the details can be found in an accepted paper in IEEE transition on smart grid. I guess I'm over time. My last message is the fact that in the area of sustainability, there are different techniques that we can actually use to either reduce the transmit power, reduce the overhead. For the uplink access example that I show you, by actually coordinating the transmission, it can reduce the number of retransmission. If we can reduce the retransmission, then we can also reduce the corresponding power consumption of the devices as well. And we do believe that many researchers believe that different types of machine learning techniques will be important for the design of networks in both wireless communication systems and also in other areas, including smart grid or power systems as well. A good approach to try. So for that, that is the end of my presentation today. And again, thank you very much for the invitation. And I welcome any questions and also comments.
Thank you very much, Professor Vincent Chang, for a wonderful talk, illuminating talk. And we have Professor Atikur Ahad. He has a question. Professor Ahad, can you please?
Thank you. Thank you, Vincent, for your, scintillating talk. So my question is about, like, when we go for deep reinforcement learning, if the dimensionality is very high due to the continuous and large change of state data. So this is a challenge. So in the IoT sensor domains or other domains, or in the wireless communication as well, this is not fixed. Sometimes it will be too much, sometimes it will be less. It's continuous and high dimensionality will be there. This is one challenge. On the other hand, is that if you have less amount of data, then also, DRL may not perform well. So how to handle these two different things, like high dimensional cases, as well as on the other hand, when you have less states and actions in the situations. Thank you.
Yeah, very, very good question. I think the first answer for your first question, my answer is that deep reinforcement learning is actually designed to handle problems which have a large state space and also a large action space as well, which can be very large. Even though in my presentation slides I only show you relatively small state space, but my understanding is that the main challenge here for either single agent or multi-agent deep reinforcement learning in particular is that the number of users has to be fixed. That is, if you try to solve a problem with only, say, 2,000 users in this case, if you increase from 2,000 to 2,100, then you actually need to train the problem again. That is actually one challenge that people try to tackle. And there are techniques related to, say, transfer learning that try to say you learn the system, you have this set of parameters, and then you actually deploy the algorithm or the system into an environment that you really don't know and see what kind of performance that you can obtain. But for your second question is, what happens if your state space is actually relatively small? In the past past 5 years in particular, one of the interesting things is that many good researchers in machine learning, they come up with different types of deep reinforcement learning algorithms. And one observation is that there's no one particular algorithm which is the best one, which is the state of the art. And some of them, if you follow the work, some of them may actually have a better performance than the other. Say algorithm A may have a better performance than algorithm B when the state space is large, while algorithm B may actually have a better performance if the state space is actually small. And there are a number of survey papers actually highlighted this particular fact. We do not really know why that is the case, because the way you actually come up with the corresponding architecture within the DNA module, I would say is an art. It also depends on what specific problem that you want to solve. But those are good
Thank you.
questions.
Thank you very much. Yeah.
Thank you very
It's
much.
wonderful.
Thank you. A round of applause for Professor Vincent Chang for being with us and for illuminating us. I hope in the coming days we will have further opportunities of meeting you in the soil of Bangladesh. Thank you. A round of applause for him. And we have run out of time. So the next session is knocking at the door. I thank Green University of Bangladesh and Professor Razak for giving me the opportunity of being in this session. Thank you. Thank you. Thank you, Professor Wong.
Thank you.
Thank you, sir. Thank you, sir. May I request rapporteur to show the certificate?
Okay, thank you, sir. Now we request the moderator of this session, Dr. Jahidul Islam, to hand over the certificate to the honorable keynote speaker. Yeah, sure.
Yes.
Thank you.
Yes. Beautiful. Great. Okay.
Thank you, sir. Thank you, Professor Vincent Wong, for your valuable time with us. So now I would very much pleased to share our e-certificate to you, which is proudly presented to you. So thank you again, and please accept this e-certificate. Thank you, sir.
Thank you very much. Thank you.
Yeah, thank you very much, sir, Professor Kaikobat sir, and Professor Vincent. Professor Vincent, this is Abdul Razak, who invited you. Thank you very much for your valuable time spending.
I hope
with
I
our
can meet you in
students.
person in future.
Okay, thank you. Thank you very much. So with this note, we are in concluding this session. Hope to, okay. Now another certificate to Professor Dr. Muhammad Kaikobat sir for his valuable time to be with us. His presence is always encouraging for the young scientists and researchers in community. Thank you very much, sir, for your nice presentation and the time. Thank you, sir.
Thank you so much for honoring me. Thank you.
Sir. Thank you, sir. Thank you, sir.